Greetings and welcome to my new calculus channel. My name is John Gabriel. So if you happen to do a search such as y square root 2 irrational on YouTube, you'll, as expected, encounter a lot of garbage, some with millions of views, and all of these here are just basically nonsense. And as you scroll down, of course, this one here is just a common proof by Hippasus. But and also, this guy's another idiot who's not that smart. But of course, you come across a video like this now. So this video is exceptionally good, by the way. I bet you never thought you'd hear me say that, right? So, and I'll explain to you in a moment why it's exceptionally good by going through the video. But first, what I'm going to do is I'm going to talk about square root 2 and how it was discovered. Okay, so just to give you the background, the Pythagoreans were trying to measure this diagonal with the side. Okay, now this is not, this looks like shorter than this side because I don't have it in the ratio 1 to 1. But if I did, it would be exactly equal. So just imagine that they are the same length. And so if I wanted to measure in geometry the diagonal with the side, this green is also equal to the side, okay? It's also equal to the blue side. I would do that. And then I would take this part R, which is equal to that, out of S, right? And so I would just say S plus R measures D, okay? So in geometry, I'm able to measure it completely. Yeah. And that's what it means to measure D in geometry. In other words, we'll get to it now, but it's taking a physical unit, which in this case is the side, okay, to measure the diagonal and parts of the side, which is this segment here that I've just highlighted, okay, because R is part of the side. Okay, so let's continue. Now, measuring the diagonal, what normally happens is this. If you start off with the side, then basically this orange dot is going to point to the distance from the origin. So measure of the side is just 1, right? And measure of root 2 lies somewhere between this blue and red line, okay? So if you try to exceed the red line, you will obviously have a value that's greater, so that won't work. But it lies between these two lines. And so let's look at an explanation. Now, the diagonal D is measured by the side. What does this mean? It means that in algebra, this is now different to geometry. Remember, geometry can do this. It just takes, as I showed you, it just takes the side and part of the side, right? This is part of the side. That's all it does. Just takes the side and part of the side and measures that, and we're done, right? So now, in algebra, what we have to do is say, let's measure the diagonal with the unit and or equal parts of the unit. So let's say that S is divided into n equal parts, okay? And that K enumerates those equal parts of S. In which case, what we're going to be doing is measuring the diagonal with S and or equal parts of S, which is the physical unit, or in this case, the abstract unit, because we're dealing with no longer a unit whose type and size matters. All we care about is that it's already a measure. So we say that D is equal to square root 2 times S, right? At this time, we don't know what square root 2 is. So we say square root 2 S is equal to S plus Ks over N, and that leaves us with square root 2 is equal to 1 over Kn. Now, the next thing we do is we square both sides. Okay. Now, when we square both sides, what is the justification for that, by the way? The justification is that we have root 2 like that, okay? And if we square this, it doesn't actually operate on the radical inside, okay? It does nothing to this 2. You could have a letter in there or a little picture. It doesn't operate on that. So how do we know it's true? Well, I'll show you in a moment why we know that's true. And um, and then you'll understand. So just bear that in mind that this is supported, the squaring of square root 2 is supported in geometry. It has no support in algebra. So we say square root 2 is equal to 1 plus r, where r is that little leftover bit, okay? This leftover bit here. So it's going to equal to r plus 1, and we'll get to that in a moment. So simply because what we've done here is we've divided through by the s's. And since r is a remainder, then r plus 1 is equal to 1 plus k over n, which means that r is equal to k over n. Hence, it must be rational, right? Because k and n are integers. But that just goes to show you that this is problematic because geometry did not affect this result. This incorrect result is obtained by algebra, okay, by this algebraic reasoning, okay, and so k is less than n, obviously, which means that it is that little leftover part. And how do we know what k and n are? Well, normally what you see is when we try to approximate root 2, you have 1, 1/4 over 10, or 1 for 1 over 100, or 1/4 over 1,000, etc., right? So which one of these here measures the leftover part? In other words, the side plus the leftover part. So we can't really, by arriving at this equation that r is equal to k over n, we're left with a dilemma. Can we find such a k and an n for r? And if we can, this would suggest that square root 2 is rational. But it's not rational, as we know, because we can prove this in algebra. D is measured by S in geometry, but it's not the case in algebra, okay? That's the problem, you see. Here, you're saying D measured by the algebraic unit, not by S as a physical unit, okay? So the difference is this. In geometry, you just have d over s, okay, and parts of s, if you want to look at it that way, and parts of s. So let's say ks, whatever remains, in other words. So if you have right angle triangle like that, and these are equal, and this is s, and this here is s, then this part here is easily ks, right? So this is geometry. And in algebra, we say d divided by s plus k over ns, because here we're just taking a part of the physical unit, which is s, but here we're taking equal parts of the abstract unit. Remember, we're not even dealing with s anymore. We're dealing with the abstract unit. So what's the difference? Okay, so think about that for a minute, stop the video, and then continue, and I'll tell you the difference. Here's the answer. In geometry, measure is done using a physical unit and or parts of it, okay? And in algebra, the measure is done using an abstract unit and or equal parts of the abstract unit. Now, in geometry, they don't have to be equal parts, but in algebra, they do, because you need to enumerate them, right? That's the reason you have that. So we cannot prove that D has no measure by S in geometry, okay, because it does. So that's the answer. Now, the common proof that you normally see is this ubiquitous proof, which was probably developed by Hippasus of Metapontum, who was a member of the Pythagorean group. And you've all seen this. And again, the little trick here is where it says that you can actually square both sides. So how do you know that the square root of 2, that square root of 2 squared is 2? Well, this is how you know. If this is a square with sides of 1 and we draw a diagonal here and we continue to do this, then we can see that if we take this area here, it'll be a quarter of the bigger square, meaning that the bigger square must have double the area of the smaller square. Okay, so now let's go to this gentleman's geometric proof. And I'm not going to cover, let's give him a like as well. I'm not going to cover the entire details, but just show you what he does, because he starts off with geometry. Okay, so let's get there if we can. I don't know why. Yeah, so here we go. He starts off with geometry and Pythagoras, and basically gives you proof that if you continue with the Pythagorean theorem, you'll show that h is equal to a, which is what he does here. And so then he continues to show how geometrically you can arrange this as follows. So you can, for example, take your GeoGebra applet, and then you could arrange a triangle, a right angle isosceles triangle like this. And so this B, side B here, would be this side here. And if you ask how you can do it, it's very easy. Just draw a circle with this as radius, and then you can get that exact length to 5. It has to be exact. And then, of course, if you construct a perpendicular from this point, then this here turns out to be isosceles. And also this triangle here has this side and this side equal. And of course, these sides here are part of two congruent triangles, okay? And of course, this little isosceles triangle is similar to the big one. And so when he gets to the end of his proof, he reaches a contradiction in algebra, not in geometry, by the way. So he says here that, let's see if it'll just stop here now, hopefully. Okay, come on. Right, so
A and I minus B are...
Right, so he reaches this part here where he says that 2b minus a is less than a, and that's problematic, okay? And also that a minus b is less than b, because that would contradict the previous results. So, however, here, read the comments I wrote, if they're still there. I'll show them to you anyway. So I said the problem arises when you try to assign measure to a and b through the abstract unit, which is what algebra uses. Then the geometry, which is correct, contradicts the algebraic assumption that square root 2 can be expressed as a ratio or as a fraction of two integers, not as a ratio, as a fraction, because a fraction is the measure of a ratio. So the proof of Hippasus of Metapontum assumes that 2 is equal to the square root of 2 squared, because it is that way in geometry, like I just showed you earlier over here, right? Where I showed you this little illustration here. So in the geometry, there is no problem, because A, side A, is not measured by an abstract unit, but by side B. And A minus B is a part of B as expected. So there's no contradiction whatsoever in geometry. The only contradiction is the one that he made in the beginning, that A over B are integers. And so there's still a little something else I'd like to say there. It's very much an algebraic proof, which is contradicted by geometry. It's not a geometric proof of the irrationality of the square root of 2, because there isn't a geometric proof of the irrationality of the square root of 2. Basically, it's a proof that shows it's wrong because it's contradicted by geometry. So if D is the diagonal and S is the side, and of course, I've explained this stuff to you in this applet here, okay? And then we have these results. We have that this is geometric, but it does not disprove the algebraic proof. In other words, you could get something like the remainder portion being equal to k over n, but suggesting that it's rational, but it's not. So there you have it. If you're not already a member, become a member of my channel. click like, become a subscriber. You can also join members only. So the members only channel would cost $4.99 a month, and you'll get free access to most of my books. In fact, to all of them. Whereas if you're not a member, you have to buy them. So one of the books I would strongly recommend that you buy is this one here, which is The Importance of Learning the Right Way. What does division mean in mathematics, and how does it affect all other arithmetic concepts? So make sure you get a copy of this book, and it might seem simple in the sample that you view, but it gets quite detailed. So don't be fooled by that. Also, follow me on Academia, which is the site here, and you can download any of my articles for free. So just by going to my profile like that, there are many articles, and you can also join the New Calculus Discord channel, which appears in every part of my detail section. This is the detail section of my videos, so you can find it there on my channel. That's pretty much it. My name's John Gabriel, and this is New Calculus Channel. Till next time, goodbye.